All right, folks, here we kind of shift gears a little bit. We're going to introduce a brand new coordinate system. You're used to the XY coordinate system, and here we introduce what's called polar coordinates. Quite simply, here's what the polar coordinate system is. A ray determines what is called the polar axis. This point is called the pole. And then if you take your polar axis and you give it a rotation up to this spot here, that's its stopping point. And notice I have the little arrow in here to show the kind of rotation that it was given. Well, then I labeled that rotation as an angle theta. That's basically the polar coordinate system. Polar axis, pole, and then you give the polar axis a rotation. I've labeled a polar point here. And that's in general the coordinates of a polar point, r theta. So in general, polar coordinates have the form. It's not xy. It's not an ordered pair xy. The ordered pair form of polar coordinates will be r theta, where r is going to be the directed distance from the pole. And we'll see what the word directed means here in a minute when we actually plot some polar points. Theta is going to be a directed angle. I think this goes all the way back to the very beginnings of trig when we looked at angles. That if your angle has a counterclockwise rotation, we said that the angle had a positive measure. Remember, clockwise rotation, negative measure. So you know what? Why don't we look at an example here of actually plotting some polar points so we can get a feel for how this new coordinate system is going to work. Alright, here we are. We're going to plot a polar point, and the first one I have here is to plot the polar point 2, 45 degrees. Remember, this is the form r theta. When we graph polar coordinates and we look at general stuff in polar coordinate system, what we tend to do is first we're going to superimpose the polar coordinate system on top of our familiar xy coordinate system. So that'd be the x-axis and y-axis, and I have superimposed on top of my xy coordinate system the polar coordinate system. Now here's what I want you to notice. Well, first off, my graph isn't going to be the best. My polar coordinate system isn't going to be the best, but it's the concept I'm trying to get across. You see concentric circles here. So I want you to imagine that this concentric circle is a circle where every point is 1 unit away from the origin. This circle here would be 2 units away from the origin. This circle, 3 units away from the origin. This circle, 4 units away from the origin. Notice I've also drawn in some radial lines. These are just stopping points if my polar axis were given a rotation. So this is if my polar axis is given the rotation up to 30 degrees, that's where it would stop. And keep in mind, there's my pole. This is the polar axis. The polar axis always kind of starts on the positive x-axis because we're superimposing it on the xy coordinate system. So now when I'm asked to plot the point 245 or 245 degrees, here's how I do it, because I want to make sense here in a minute out of what a directed distance is. The first thing I do is I take care of my rotation of the polar axis. So since it's 45 degrees, that's a positive 45 degrees, my polar axis starts here. It would get rotated up to 45 degrees, and this is where it would stop. It would stop on that radial line. Now my r value is a 2. It's a positive 2. Since it's a positive 2, I will come out along my polar axis stopping point. I will come out along that 2 units. That's 1, that's 2. So right there, that point right there is the polar point 245 degrees. Let's try another one. Let's try plotting the point -3, 135 degrees. Okay, now notice here my r value is negative. So watch what that means. I start off by doing my rotation of the polar axis first. So I take my polar axis and I rotate it over here to 135 degrees. So my polar axis would be right here. That's its resting point after the rotation of 135 degrees. That R value being negative, that means I will not go along the polar axis 3 units, but I will go in the opposite direction 3 units. So if my polar axis is stopped here with an R value of -3, I would go this direction 3 units. 1, 2, 3. So that's the point -3, 135 degrees. That's why I stress doing the polar axis rotation first. So just note right now, polar axis rotation, if the R value is positive, the directed distance is positive, wherever your polar axis stops, then you go along the polar axis that many units, R units, to plot the point. If that R value, the directed distance, is negative, wherever the polar axis stops, you go in the opposite direction of the polar axis. Let's do one more. Let's plot the point, -2, 225 degrees. All right, so here I'm going to do the polar axis rotation first. So my polar axis gets rotated to 225 degrees, so it would stop right here along that radial line. So that's where my polar axis has stopped. The R value is -2. So that means I go in the opposite direction of where my polar axis stopped. I don't come this way 2 units. I go in the opposite direction 2 units. That point's already plotted. That was what we plotted in part A as being the polar point 2, 45 degrees. Now we found a polar representation for it as -2, 225 degrees, which is correct. Well, they're both correct. You know, part C illustrates something about polar coordinates. Polar coordinates are not unique. There are this one polar point here. There are an infinite number of ways to represent that in polar coordinates. You could just simply keep adding multiples of 360 degrees to the 45 as a for example. But I want you to remember that polar coordinates are not unique. So that's a quick example of how to plot polar points. Next up is, since we superimpose the polar coordinate system on top of the XY coordinate system, we should be able to come up with a way to relate polar coordinates to our rectangular coordinates. And that's what we're going to look at here in a minute. All right, here we are. We're going to try to figure out a relationship between polar coordinates and our familiar rectangular coordinates, the X and Y coordinates. As the last example showed, we like to take the polar coordinate system and superimpose it on top of the rectangular coordinate system. So let's check out this picture I have here. Here's our familiar XY, the rectangular coordinate system. Here's my polar axis, and there's the pole. So I've sketched in, the polar axis rotating to here. That's its stopping point. And this would be this would give me the coordinates of this point, that polar point, of being r theta, where we know from here to here, that's the directed distance, that's our r value. In rectangular coordinates, the rectangular coordinates of this point be xy. Which means, this side is x, this side of the triangle is x, this side is y. So now we can just use a little bit of our knowledge of trig. For example, look at this angle. I'm going to go back to right triangle trig. The cosine of theta, the cosine of that angle theta. Well, we know cosine is, it's a right triangle, we know cosine is adjacent over hypotenuse. So here's theta, x is the adjacent side, r is the hypotenuse. We also know sine theta. Well, sine theta is opposite over hypotenuse. The opposite over hypotenuse. Y over r. And if I multiply both sides of this equation by r, I get cosine theta. I get r cosine theta is equal to x. If I multiply both sides of this equation by r, I get r sine theta equals y. And we've come up with two important formulas on how to convert from polar to rectangular, rectangular to polar. So let me put them over here. X is r cosine theta, y is r sine theta. This is what we're going to use to convert from polar coordinates, because that's when we know r and theta. When we want to convert from polar back to rectangular. Now if we have rectangular and we want to convert it to polar, well, let's look at this triangle. It's a right triangle. We know the Pythagorean theorem says x squared plus y squared equals r squared. So let me write that down. X squared plus y squared is equal to r squared. And then, well, you know, we looked at the cosine of theta, we looked at the sine of theta. What's the tangent of theta? It's opposite over adjacent. Tangent of theta, opposite over adjacent. So tangent of theta is y over x. This, I need you to know this, folks, on how to convert from the first line here is how to convert from polar to rectangular. Second line, this will tell us how to convert from rectangular to polar. So let's look at a couple of examples of how to use these newly developed conversion formulas, if you will. All right, hey, here in the first example, I've given you a polar point, and I say, hey, let's convert to rectangular coordinates the polar point to pi over 6. So this is a point in polar coordinates, and we're going to convert that back to rectangular coordinates. To do that, you just need to know that x is r cosine theta and y is r sine theta. That's just a matter of substituting in and just doing the math. R is 2, theta is pi over 6. So you have x is 2 times cosine of pi over 6. That's 2. Well, the cosine of pi over 6 is, see, from my unit circle, I know that's square root 3 over 2. And 2 times square root 3 over 2 is square root 3. For the y-coordinate, well, the sine of pi over 6, we know the sine of pi over 6 is 1/2. 2 times 1/2 is 1. So the rectangular coordinates, put it together as rectangular coordinates, would be square root 3, comma 1. So this polar point converted to a point in rectangular coordinates would be square root 3, comma 1. And that's all there is to it when converting from a polar to a rectangular point. Next up is we're going to convert a rectangular to a polar, and that's just a little bit more involved, but it's not too bad, as we'll see here in a minute. All right, hey, in this example we're going to find, notice here I want to find two polar representations. And I have up here where the angle theta is between 0 degrees and 360 degrees. I could have it as 0 to 2 pi. I just decided to do degrees for this example. And the point that we're going to convert to polar is the rectangular point 2, 3. Now, believe it or not, the first thing I do for a problem like this is I just quickly plot my point. That's my point 2, 3. And you'll see why I think plotting the point helps. I think you'll see why here in a minute. All right, now let me get on with it. I have my point plotted. I need to use the formulas x squared plus y squared equals r squared. And tangent theta is y over x. Well, you just substitute in. You know, x is 2, y is 3. So you'd have a 2 squared plus a 3 squared is equal to r squared. 4 plus 9 is r squared. 13 is r squared. Take the square root of both sides, and it's important to remember that r is plus or minus the square root 13. I don't know which value I'm going to use for r until I know what my theta value is, what my angle is. I don't know which directed distance to use. So let's go over here and let's find what theta is. Tangent theta is y over x, so that's 3 over 2. And I don't know what that is off the top of my head, but I do know how to find this angle. I use angle finder, inverse tangent. And let's see, inverse tangent of 3/2 is 56.3 degrees. Pretty close to 56.3 degrees. So I think I can find one polar representation immediately for this point. And that's when I take my polar axis and I rotate it up 56.3 degrees. Then my directed distance is positive square root 13. So let's write that down. Square root 13, 56.3 degrees. But notice I want to find two polar representations. All I have right now is one. Now my second polar representation, and I have to satisfy theta being between 0 degrees and 360 degrees. That prevents me from just simply adding 360 to this, because that would be more than 360 degrees. I think my second polar representation is going to use this negative square root 13 as the directed distance. It's going to use negative square root 13 for r. But now what's my theta value going to be? So here's what I have to figure out. I have to get my polar axis, I have to rotate my polar axis to a spot about right here. So I need my polar axis to rotate to about right here, so this would be its ending point. And then if this is its ending spot, the negative r will bring me back out to here. So how am I going to figure out this angle? Well, doesn't it look like my 56.3 degrees and whatever this angle measurement is here makes a line, makes a straight angle? Remember a straight angle, 180 degrees? So it seems like all I have to do is add 180 degrees to this 56.3 degrees, and that gives me 236.3 degrees. I just simply add 180 to this. So I have now come up with two polar representations for the rectangular point 2, 3. The square root 13, 56.3 degrees, and negative square root 13, 236.3 degrees. Let's do one more that's just a little bit more involved. All right, folks, same directions as the last example. Let's find two polar representations where my angle theta is between 0 degrees and 360 degrees for the rectangular point 2, negative 3. First thing I would do is I would plot that rectangular point. So there it is. Alright, now I just proceed like I did in the last example. X squared plus y squared equals r squared. And tangent of theta is y over x. So we have a 2 squared plus a negative 3 squared is equal to r squared. 13 is r squared, plus or minus the square root of 13 is r. Remember the plus or minus. Here we have tangent theta is negative 3/2, so we know theta is the inverse tangent of negative 3/2, and if I use my calculator, I get inverse tangent of negative 3/2 to be about negative 56.3 degrees. And I can't use that. I can't use this theta value because it's not between 0 and 360. Now think about why this happened and what happened and the importance, I think, of just quickly plotting the point. Over here, when I knew I was going to have to use inverse tangent, I remember back to when we studied inverse trig functions, and I knew inverse tangent's going to find an angle for me on the right half of the unit circle. As soon as I saw where this point was plotted, I knew the calculator was going to give me that angle measurement right there, a negative angle. And I knew I wouldn't be able to use it. But I'm still going to come up with two polar representations for this point. So let's think how easy this could be. The most straightforward, immediate, hey, let's find this right away. Get the angle that's coterminal with negative 56.3 degrees. That is, just simply add 360 degrees to this. If you just simply add 360 degrees, it's going to give you that angle measurement there. So it's going to take your polar axis and it's going to rotate it to this spot. And when you rotate it to that spot, you then would use the positive r value. So square root 13. And if I take negative 56.3 degrees and I add 360 to it, I get 303.7 degrees. But we're supposed to get 2, so we have to get 1 more. Well, that other polar point representation should occur when our polar axis would stop right here. So we'd give it a rotation to here, and then if that's where my polar axis stops, to get to this point, I would use the negative square root 13. Well, let me get that written down, negative square root 13. Now how am I going to figure out this angle measurement there? How am I going to get that angle measurement? Well, quite simply what I would do is I'd take this negative 56.3, and just like I did in the last example, I would just add 180 to it. So I just simply take negative 56.3, add 180 to get 123.7 degrees. And there would be the two polar representations for this point. So hopefully you see why it seems silly to plot the rectangular point, but it can kind of help give us guidance on making sure we get the correct answers. And that's it for this example. All right, hey, after we just took a look at how to convert points from rectangular to polar or polar to rectangular, the next step is let's take equations and let's convert rectangular equations to polar equations, or polar equations back to rectangular equations. So my first example here is, here's a rectangular equation. Let's convert that to a polar equation. This one's pretty straightforward because we know x squared plus y squared equals r squared. Let me just write those, conversions over here real quick. Those are the 4 conversion formulas you need to know. We know x squared plus y squared equals r squared. So we're trying to take this rectangular and convert it to polar. Well, that's simply r squared. So r squared equals 16. That is the polar equation. Now what you could say here is you take the square root of both sides and you would get r equals plus or minus 4. That would be fine. You could even say, and you'll see why in the next section when you start graphing polar equations, you could just simply say r is 4, or you could say r is negative 4. The preferred would undoubtedly be the positive, r is 4. And think about why. If I tell you, sketch the following graph, r equals 4, and you know r is the directed distance from the pole, you would know to plot or to graph r equals 4, you're just simply going to plot every point that is 4 units away from the pole. And if you plot every point that's 4 units away from the pole, you're going to end up plotting and drawing a circle. You're going to draw a circle that has a radius of 4 and it's centered at the origin. That's what that rectangular equation says. You know, and that's saying the same thing as plot r is -4. For any given theta, you would go in the opposite direction. You're still going to get a circle that's 4 units away, a circle where every point is 4 units away from the pole. That's a friendly one to convert from rectangular to polar. Let's look at this one. Y is equal to 1. Oh, you know, that's a nice horizontal line in the rectangular world. Y is equal to 1. Now I want to convert that to a polar equation. Well, it looks like the only thing I have to work with is right here. We know y is r sine theta. So let's just put r sine theta in there for y. And then I would divide both sides of this equation by sine theta to get r equals 1 over sine theta. And if you want, you could say, well, hey, Bill, that's the same thing as cosecant theta. Yeah, you're correct. But the key is I'm able to have it as r equals something. You know, I'm setting the foundation for what you're going to do in the next section when you're going to start graphing polar equations. It's nice to have them in, if at all possible, to get it into the r equals form. Because once I have it into the r equals form, it's going to be easy to graph because I have a graphing calculator. But for this one, y equals 1, substitute r sine theta for y, and you could either have this as a polar equation or this is the polar equation. Let's do one more. Give me a second here to kind of erase. So just one more conversion. 3x plus a 5y minus 2 equals 0. Well, quite simply, wherever you see an x, you're going to put in an r cosine theta. Where you see a y, you're going to put in an r sine theta. So that gives 3r cosine theta plus 5r sine theta minus 2 equals 0. And like I just showed in part B, if I could get this into an r equals form, you know, I'm going to do it. And I think I can here. It's not that bad. I would start off by adding 2 to both sides of the equation. And then after I add 2 to both sides of the equation, over here on the left side, you know, I can factor out the r. And then once I factor out the r, I can divide both sides of the equation by this 3 cosine theta plus 5 sine theta. And that's where I would stop. That's my polar equation that's the same as that rectangular equation. So there's 3 examples of how to take rectangular and convert them to polar. So we're going to conclude this video with a quick look of how do you take a polar and convert that to rectangular. That's the next example. Here we are, folks. We're going to take this equation, it's a polar equation, and I want to convert that to a rectangular equation. So that means I want to convert it into a form where I see x's and y's. So what I have r equals 2 cosine theta. And it's like, wow, boy, what could I do here to make this friendly? If only I had an r right there. If only I saw 2r cosine theta. Because if I saw an r cosine theta, I would know r cosine theta is an x. So what could I do to get an r in there? Legally, what could I do to get an r in there? That's right, just multiply both sides of the equation by r. If I multiply both sides of the equation by r, I get r squared is equal to 2r cosine theta. Now I'm feeling pretty good because I know this r cosine theta is x. And hey, check it out. What's r squared? Well, r squared is x squared plus y squared. So all I have to do is r squared is x squared plus y squared. That's it. That's a rectangular equation. And, you know, I'm going to stop here. I know some people would say, oh, hey, why don't we subtract 2x from both sides? Fine, there's nothing wrong with that. But I have a rectangular equation right now, and I feel that's a good place to stop. And for me, that's where I'm going to stop. So I hope this introductory section of, you know, the wonderful world of polar coordinates is making sense. And hopefully you're going to be ready to do some graphing in the next section. Thanks for watching.